All right, class, where we are now is to talk about the neuron action potential. The neuron action potential. And then after this, we'll talk about the muscle action potential. It'll be easier once you understand the details of the neuron action potential. All right. Action potentials form the basis of nerve and muscle conductivity. This conductivity allows charges to move along the membrane, similar to how electricity moves along a wire. Action potentials have some similarity to a resting membrane potential, but many dissimilarities. The similarity is that ions, sodium and potassium, travel through transmembrane integral proteins. They travel through gates down their concentration gradient by diffusion. The dissimilarities are the gates are always closed and only open when the proper voltage, known as threshold voltage, is applied to the cell membrane. Okay? Each ion have their own specific gate. There's a sodium gate and a potassium gate. The gates are slightly larger than the passive leak gate, so ions can move through faster. Okay, here's some preliminary information to know about the neuron action before we get into the details of it. The cell membrane is considered to be polarized. Okay, it's called polarized. The outside of the cell is a positive pole and the inside is a negative. So those terms are going to come up. So it's kind of like it's polarized. The outside positive, the inside negative. Okay, as you can see here, outside positive, inside negative, let's say. Okay, outside positive, inside negative. The voltage-dependent transmembrane channel for sodium has two parts to it. And this is a good picture of that right there. It has two parts to it. One part of it is called the activation gate, and the other is the inactivation gate. The activation gate and the inactivation gate. Now, they're both in front of one another. Now, I don't know how many of you, I always use this in class, have been to that Macy's in Humble, the Macy's in Humble, in the shopping center. And there are two doors on that side entrance. You go in the first door, then a little farther, then the second to get into the store. So both doors must be open to get into the store. If one door is open, the other is closed, you can't. So realize that both doors, activation and inactivation, must be open to get in, for sodium to get in. Okay. So the voltage-dependent transmembrane channel for sodium has two portions. An inactivation part that is always open at resting membrane voltage. So you see the inactivation one, see that's it's open. This is doing resting membrane. At resting membrane potential, let me say it again, at resting membrane potential, which we just talked about, the inactivation gate is open. So sodium could go through, but the activation gate is closed. The activation gate is always closed until threshold voltage is reached. When threshold voltage is reached, the activation gate quickly opens. This is going to pop open. And the inactivation gate slowly eventually closes. And the inactivation gate slowly eventually closes. So when threshold is reached, the active quickly opens and the inactivation gate slowly eventually closes. I'm going to make that a little differently. I'm going to say slowly eventually closes. Like I say, I'm editing this as we do it. Slowly eventually closes. I like that better. Okay? All right. The same voltage that opens the activation gate and closes the inactivation gate also causes the open of a voltage-dependent gate to potassium, but it is very slow to open and close, and we'll come to that. The action potential is all or none. This means the voltage height of the action potential. See this, when we do the action, this is the voltage height. We'll talk about it. The voltage height of the action gets no higher despite the magnitude of the threshold voltage. See right there, when we get to it and put it in play, that's threshold voltage. What it means is, if the threshold voltage, in this case, you had a negative 70, you got a negative 55. So what's that, 15? If the threshold voltage was a positive 15 millivolts to do it, but you gave it a positive 40 millivolts, this height would not get any higher. If you don't give it to 15, you won't get any of this. If you give it greater than the 15, if you give it to 15, you'll get this. If you give it more than the 15, you'll give it this. So it's either you don't get it or you get it all. You don't get it or you get it all. And that's all or none. This means the voltage height of that gets no higher despite the magnitude of the threshold voltage. If the threshold voltage is a positive 40, in this case it was a positive 15, then no action potential will be created as less than 40 is given. So whatever the threshold is, this is 15, then that's what it's going to be. And you will not get any higher. This is called all or none. We'll talk about that. The total duration of an action potential is, let's say, about a millisecond. The action potential graph has time in milliseconds. That's on the x-axis. And on the y-axis is voltage in millivolts. It's voltage in millivolts. Okay. So that kind of, so keep reading this document. That gives some preliminary information. Okay. So now I'm going to, and we may have to break this video up, steps of an action potential. So we'll be using this, and this picture. All right. So let's start out with the cell membrane initially at its resting membrane potential, which on here would be that right there, and here, this right here. We've already discussed resting, so on this would be number 1 on this here. Okay. A voltage stimulus is given to the membrane. Now, if it's in your body, it's given by your brain or something else. If it was in a lab, we would put a battery to this. If it was in the lab, we'd hook a battery to it. And we'd use a battery because it'd be artificial. We'd have taken the neuron out. Okay? A voltage stimulus is given to the membrane that allows the cell membrane to reach threshold at one location along the membrane. Now, first of all, before we do this, I want to come here. In a neuron, we have dendrites, a cell body, and an axon. I'm going to come over here to this picture. In a neuron, now we're going to get to neurons later in an official chapter, but in a neuron, you have dendrites. Dendrites bring the signal into the nerve cell. Dendrites bring the signal in because they would be hooked to something. Here's the cell body, and here's an axon. I'm doing it with the axon. The reason is axons generate action potentials. These other areas do not. Axons generate nerve action potentials. So I'm using the axon to do this. The axon. These other areas do not. They generate a graded potential, which we'll talk about a little later in this document. So we're taking a piece of the axon, which is this. That's why I put that right there. So this is happening right there. Now what we're discussing, this is happening in one little spot of the axon. Just one little spot, let's say, of the axon. So we're not talking about conductivity yet. We're talking about just one action potential. Okay. So I go back. Here's that picture. The cell membrane initially is at resting membrane potential. A voltage stimulus is given to the membrane that allows the membrane to reach threshold voltage. Let's say this is threshold voltage here. Let's say that's, see this? Okay. And let's say here's threshold here. Okay. To reach threshold voltage at one location along the membrane. Remember I said it's just one spot that this is going to happen. The threshold voltage causes a quick opening of the activation gate. And let me come in here so you'll remember. Causes a quick opening of the sodium activation gate. Let me help you out here. Of the sodium activation gate. Okay. And causes the sodium inactivation gate. Remember, we discussed that. The sodium inactivation gate to slowly close. Now, this is the situation here. Okay. Because the activation gate opens quick, and that same voltage at that same time tells the inactivation gate to close, but it's slow, there's going to be a point in time that both gates are open. Because both gates are open, sodium is going to rush in. Now remember what we talked about. Sodium rushes in not only by charge, but by diffusion. And these gates are bigger. They're larger than the passive leak channels. So sodium comes rushing into the inside. What charge does sodium have? Positive. So I'm going from a negative straight up to a positive. See how quick this is moving in? It's almost moving in at the same point in time. Instantaneous. See how quick it's moving in, and see how little time difference is happening? Okay. Now, since you remember, this was the inside was negative, but now as you move positives in, the inside starts going towards zero, because the inside now is starting to get more positive. Because now you're moving this way, you're taking the charge off the membrane. That's what they call depolarization. That's what they call depolarization. Now, however, you get to a point right here. When you get above that line, not splitting hairs, you really have reverse polarity. When you get above that line, let's go here. When you get above that line, look what has happened. This is just a little picture. You reverse polarity. Now the outside in that one spot is more negative to the inside. You reverse polarity. Okay, we go back. But they still just call it depolarization, even though the minute you move above here, you reverse polarity in that one spot. Okay, so let's go to number 4. Around the time that the inactivation gate finally closes, see, remember it was slow. Around the time the inactivation gate finally closes, disallowing any further sodium ions to enter the cell, the potassium voltage dependent gate opens and potassium begins to flow out of the cell. Now remember, potassium was an ion in higher concentration inside the cell than outside. Remember that? So when you open the gate, potassium starts coming out. If potassium starts coming out, then things start becoming more negative because potassium was positive. So this is called repolarization. Repolarization. So potassium is starting to come out. So you reach threshold by some means. You open, you start to open, when you reach threshold, you quickly open the voltage activation and slowly close the voltage inactivation. Both gates are open. Sodium rushes in, depolarizing. And ultimate goes to reverse polarity, but we won't say that. Then you reach this point right here. Now, when you reach here, the question would come, has sodium reached equilibrium? No. The reason it stopped is because there was a lot more sodium wanted to come in. Listen to me. A lot more sodium wanted to come in. The reason it stopped is because the inactivation gate closed. And that stopped it right there. That stopped it. That's why the thing is all or none. It's because it's already set in the gates as to when it's going to close. It has nothing to do with how much sodium wants to come in. Then about the same time that the sodium inactivation gate is closed and the potassium gate opens, it's slower. See, in duration it's slower. But when potassium gates open, potassium comes out. Now it was slow to open and it's slow to close. But at that point you're repolarizing. The potassium gate was slow to open and it's slow to close. Thus, more potassium comes out than should be. See, by the time the potassium gate opens and then finally closes. Now, in other words, it's the same signal, threshold. It's already set in the gate. The gate will open for a while and then close. You don't have to do anything else. When it finally closes, it overshoots some. So that gives more potassium out than normally would have been. More potassium out than normally would have been. That's hyperpolarization. Then I need to get back to resting membrane potential. How do we do that? We go back what established it. The large molecular anions and the sodium-potassium pump. So what gets us back to RMP are the large molecular anions and the sodium-potassium pump, which we talked about earlier. We'll close here.